ladies and gentlemen. A very good evening to the last evening plenary session of this IAC 2015. We will have 1 hour at the end of this intensive conference day to talk about Orion's, or MPCV as some of you know it, Exploration Flight Test number 1, and the scope and goals of the entire program, going beyond Earth orbit and taking human spaceflight beyond LEO for the future of human spaceflight, at least, if not mankind. With me, I have two guests here on the stage, and I'm very happy to welcome William Gerstenmaier, or Bill Gerstenmaier, who is the associate administrator, one of the associate administrators of NASA. He will talk to us about the scope of the program from a NASA point of view. And I also have with me here on stage Mike Hawes, Vice President and Program Manager of MPCV Orion from Lockheed Martin. And he will specifically elaborate on the actual progress of the program and the first test flight. My name is Christian Bank. I'm Senior Manager of Airbus Defense and Space, formerly known as EADS Astrom Space Transportation in Bremen. And I welcome you again to this session. So, I think in the course of the IACs of the past years, we have seen the MPCV Orion program in various stages. We've talked about it in various presentations, overview sessions of governmental programs. And I think it's a very good time now in the program to see what are the program objectives and the ambitions of that program that go much beyond just LEO and the ISS. That is our bread and butter activity nowadays. Maybe I can ask Bill Gerstenmaier to tell us a little bit more about the program itself, its ambitions from NASA point of view, and the steps we are taking right now, that we are witnessing right now.
Okay, thank you very much. It's my privilege to be here, and what's really exciting is for this session, you get to see real hardware, you get to see stuff that's flying, and it's not concepts, it's not things we're talking about in the future. These are things that are really operational systems that are ready to go fly. This was a test flight, again, it was uncrewed. Its purpose was really to look at the heat shield performance predominantly, also look at flight control, but it also validated all the systems going uphill, all the separation systems, and also all the parachute systems that occurred during reentry. So this was a real test of the Orion concept, the real test of the Orion systems to see where they are. This vehicle fits in the broader scheme of things. It's going to be used for deep space. It will be our vehicle used for the next multiple decades for crew transportation into deep space beyond low Earth orbit. It can handle a crew of 4 for 21 days, which makes it a very nice vehicle for doing things in the vicinity of the moon and augments well with other countries that are planning on doing things around the moon. So it's exciting to see this flight come together, see the hardware come together, see the teams come together, but maybe more importantly for me, to see the reaction in the United States to this flight. This is the first time we've been significantly beyond low Earth orbit with a manned or crew-rated vehicle, a vehicle that's ready to go beyond low Earth orbit, and the excitement from the community was absolutely amazing in the United States. And that shows us that there's a real hunger to go do the exploration, to go do the things that you're all talking about here at this conference this week. So it's exciting to see the public behind us, to see the excitement. They're ready to go. I think they want us to work at a faster pace than we are. We're working as fast as governments and funding can allow us. If you don't mind, I think we could go ahead and show the video now. I have a short video, and then Mike can do some opening remarks. Mike also has a video. There'll be some overlap between the videos, but I think it's good for you to see the videos and see what we're doing and see what's happened during this flight. So if you could roll my video, please.
Go. FIDO.
Go.
Guidance.
Go.
LSO.
Go.
Weather.
Go.
Pointing.
Pointing's go.
CDH.
Go.
GNC.
Go.
Ecom.
Go.
Inco.
Go.
NGC.
Go.
Engine start box, go.
Rock report, range status.
Range green.
Upper stage LH2 securing flight level. Status check.
Go Delta.
Go Ryan.
5, 4, 3, 2, 1.
And liftoff at dawn, the dawn of Orion, and a new era of American space exploration.
Flight FIDO.
Go FIDO.
Yes, sir. Just passed through apogee. The altitude was 3,132 nautical miles.
Thank you very much, Bill, for sharing this video with us and demonstrating, even for the last skeptics, that this is really something substantial that has taken a stage which goes much beyond paperwork, and we're really talking about a very substantial program and substantial progress, which NASA had announced a couple of years ago already in various stages. It has undergone redefinitions over the years, but so much the better to see now things happening. And I think part of it is devoted to your industry, actually. And so this is why I'm very happy to hand over to Mike now to tell us a little bit more what you experienced from your side with your industrial team, with your people working on it, how this all came into being, and where we are today.
So Bill alluded to the primary goal of the tester. What I would say what drove the flight profile was wanting to investigate the heat shield. The heat shield is a material that NASA had not used since the Apollo timeframe and actually had to be reformulated, and so we learned a lot about that process. But in structuring the flight, we were also able to actually test and mitigate 13 or so of the top 17 risks in the program. And Bill mentioned some of those along the way. We also got an opportunity to learn a lot about the manufacturing of the spacecraft. This is actually the second pressure vessel of a flight type pressure vessel that we've built. We're building the third one right now in the Michoud Assembly Facility outside of New Orleans, Louisiana. And we've gone from a metal structure that started with 33 individual welds to one that now only requires 7. And we're already well into that welding process today. So we have another short film clip to do, and we'll make sure, I'm not 100% sure which one this is. I've seen that one a couple hundred times so far. It's actually one I really like. But the next one, I think, is one that actually you're picking up the acoustic data from the microphones. We flew microphones on the spacecraft to get acoustic data. And so you're actually going to hear the separation of the panels. You're going to hear the thrusters pound. You're going to hear the parachutes actually pop. And you're going to see more of the plasma that builds up around the spacecraft on re-entry. We're looking out the tunnel window at the top of the spacecraft. Okay, I guess I was a little mistaken which one we provided, but let's talk about some of the events that you saw now in both of those movies, and Bill referenced some of them. Some of the most critical events are actually the separation of all those components. So you saw the panels that provide structural support around the service module come off and separate. You saw the jettison of the launch abort system tower. So once you're above the Earth and no longer need to have the escape system to pull the capsule off the launch vehicle, you want to get rid of that launch abort system so you're not carrying that weight. So you saw that. You saw the separation of the actual capsule from the service module. And then as you re-enter, the parachutes are actually protected by a cover on the top of the spacecraft. You saw that come off with its own parachutes. And then you saw all the parachutes separate, 2 drogue chutes, and then pilot and main chutes for landing. In that, you saw the chutes. The chutes are all, because we're collecting engineering data, the chutes are all different colored patterns, and they're all different colored risers on the chute so that you can know exactly what's happening for each individual chute. And that's part of how we're collecting the data. It's not just the sensors in the system. A lot of it is the video that you take and the acoustic data that I mentioned. So you actually had an opportunity to see many of those risk events that we wanted to talk about and we wanted to test happen there in the video.
I think another thing that's really important is you also got to, you didn't get to see it, but we got to see the actual performance of the avionics in the radiation environment. If you saw the graphic where we went the 2 orbits around the Earth, we went through the Van Allen belt several times, and you can see the radiation environment increase on the spacecraft. We kind of expected to see some single event upsets in some of the avionics and some of the computers. We didn't see any, which I guess we saw 2 small ones. Mike's helping me here. But it was less than we had anticipated, which was a good finding for us and shows the strength of the avionics system that the teams have chosen.
Yeah, we actually didn't see the upsets in the computers, which is where we would have felt they might occur. A third system called the video processing unit showed resets. The one time it totally reset itself, just as it is programmed to do. The second time I would accuse my old MCC friends perhaps of jumping the gun, and they ground commanded the reset rather than let the processing unit do it themselves. So actually it was good because then we validated the whole ground command path to the space station process. So there were lots of things that we got out of that. The one thing that I will notice or note for you on this flight that Christian knows well is that the service module for this flight was really just a piece of structure to simulate the mass of a service module. When we fly the next time on the Space Launch System, it will also be with a service module provided by ESA and Airbus. And so the next flight is 2 really big changes in that we fly on the Space Launch System and we fly with an ESA-provided service module.
I think the other thing we saw that was intriguing to me, at least, was also the GPS performance was very good and very solid all the way up even to this far distance. We expected, again, maybe not to see quite as many satellites as we were able to still see and digest for the receivers. The entry performance was also really good from a propellant standpoint. It used less propellant during reentry, and it just wasn't a standard reentry. There is a little bit of lift vector in this vehicle, even though it looks symmetric. So they actually steered the vehicle and changed the center of gravity such to generate a little bit of lift during the reentry to actually go look at performance of the system to verify that the capsule actually flies the way it should fly in real flights. So you see this as kind of a demonstration, but I wanted you to know that there's a lot more behind this demonstration than is apparent just in the video. We were stressing systems, we were pushing systems, trying to understand everything we could learn out of this test, because these tests are tremendously valuable to us, they're tremendously costly. So we want to make sure that every aspect that we can learn from this test, we learn. So then when we get ready to go fly Exploration Mission 1 with the European Service Module, and then we get eventually to crewed flights, we've worked out all the bugs, we've learned all the things we can learn through this test. So again, I think you don't see it in the video, but you sure can see it in the telemetry, and you can, and as the teams pour over the data, they're learning more and more things, but what's really encouraging is they're really validating how solid this design is for this capsule, which is really good.
And we talked about the heat shield test, and you notice now looking at the spacecraft is that the heat shield material, the AVCOAT, is used just on the bottom. The sides of the spacecraft use tiles that are very similar to space shuttle tiles. And in fact, if you go past the Lockheed Martin booth right behind the auditorium, there are 4 of those tiles that are actually from the flight vehicle on display there at the booth.
Okay, thank you very much. That already explained a lot around the videos, things which were running in the background that could not be seen so explicitly in the video, and I'd like to iterate a little bit with you on the test that happened before. This was, of course, a very emblematic and very visible flight test, but there were a lot of things which were done before and another couple of things that you mentioned that will come after. But before we enter into these kind of details, I would like to let the audience know that we are happy to receive questions from your side as well. If you want to ask some specific questions, there are people from the local team, as one lady waving up there, who have prepared some papers, so please put down your questions on these papers. They're going to be collected and be delivered to us here. So as we walk through the various stages of that mission and the various aspects of that program, we'll try to answer some of these questions as well. So please don't hesitate to come forward with your questions. Okay. As you mentioned, a couple of subsystems already and how much they were stressed and pushed to the limits. I think one of the things that may be interesting is actually how much does that re-entry profile compare to the future re-entry profile when coming from something beyond low Earth orbit. And I think you already mentioned the performance of the heat shield, but it should be interesting to give again a comparison. You have a very special flight profile, a very high elliptical orbit chosen, and I think that contributed to the making that test as realistic as possible.
So the desire or the driving factor for the flight test again was to put as much stress on the heat shield as we could. We were targeting to get as close to as a lunar mission re-entry as we could. And with the flight profile that we had off of that Delta IV Heavy that you saw in the movies, we actually reached about 84% of a lunar re-entry speed. And so that helps us, and it's not just the performance of the vehicle, but it's the ability to take that data and then sync that to all of your models and all of your simulations. And so we were able to do that in many areas of the capsule through doing the test flight. The other thing that's somewhat unique about the test was that the way that NASA actually chose to contract with Lockheed Martin to do the test was very unique. They actually set the contract up to say that NASA is purchasing data. You, Lockheed Martin, go conduct the test. And so we actually purchased the launch vehicle from United Launch Alliance. We ran the mission management team function with both Lockheed Martin and NASA folks represented. But we also chose to make use of NASA teams in ways that will be their long-term roles, rather than build up a unique Lockheed Martin team to try to go do those things. So we were able to use the mission control folks in Houston that will be controlling all the other flights of Orion. We had them control this flight as well, even though it was largely run by the computers. We had a whole series of activities with the mission control team. The ground operations team, we actually build Orion in Florida. We took over a NASA facility, now referred to as the Neil Armstrong Operations and Checkout Building. And we actually build the spacecraft there. The structure is built in New Orleans. Everything else happens in Florida. And so we built all of those processes. We then turned the stacked capsule over to the NASA team and working with United Launch Alliance for the stacking of that process, for the checkout for the launch. And the NASA team will do that on the next missions. And so we were able to start developing the people side of the interfaces too, and the teamwork aspect of it. The Kennedy folks as well were the interface to the United States Navy. So the whole recovery process, the use of the well deck ships, all of that was just as it will be for future flights, but we were able to exercise it early in this flight test as well.
Okay, thank you. Talking about crewed flights, you mentioned the next flight, which will incorporate a fully functional service module. But I think this is still unmanned. So let's look a little bit ahead of that. Bill, could you maybe tell us a little bit more about the planning for the future manned flights? What is NASA planning? How does that fit with the SLS developments or the launcher system, which is going on in parallel, so that we understand the far perspective?
Okay, so kind of the big picture plan ahead of us is the next flight will be, again, an uncrewed flight, but it will be on a SLS with an interim cryopropulsion stage for the upper stage. It will have the European service module fully functional underneath, and we'll take that capsule without a crew to a distant retrograde orbit around the moon, and then we'll return from that distant retrograde orbit and again get to see vehicle performance. So what we'll get to see in this regime is we'll get a chance to see how the spacecraft actually operates in deep space. We'll see how the accuracy is of insertion into this distant retrograde orbit that's stable for a significant period of time. We'll get a chance to see the return out of that distant retrograde orbit and then get to see the full entry velocity, return on the heat shield again, and see overall vehicle performance. So this will be kind of an end-to-end checkout of all those systems. What will be missing on that vehicle are the things associated with the crew. So there won't be a life support system for the crew because there's no crew. There won't be crew displays, there won't be crew seats, but we'll be able to get some radiation measurements, some things inside the capsule to see how things perform. And then on exploration mission 2, it will then be, again, now a full-up capsule with crew on board. And again, we'll probably go around the moon at some place after some checkout in low Earth orbit, but it'll be exciting to see those pieces come online. And this exploration mission 1 will be the real checkout test for the service module that the Europeans are building. This, if you think about it, the service module is the ability for this capsule to get into orbit and out of orbit. It provides all the control functions. It also provides radiators for cooling, provides solar electric power back to the vehicle. It's a very sophisticated spacecraft in itself, and it'll be great to see this European module actually operate and work with Orion. So that's what the teams are off busy doing now. The structural test article is being manufactured in Europe. It'll get shipped to Plum Brook in Ohio probably next month, the middle of the month or so, and it will begin structural testing in Plum Brook. So again, a lot of work going into these processes moving forward, but that's a general ploy or plan as we go from EM1 to EM2, and then the idea is after EM2 where we have a fully certified crew-ready system, and then we'll try to pick up a series of missions around the moon, roughly maybe once a year, using the Orion and SLS systems to do more and more demanding tests in the proving ground to space somewhere around the moon.
Very short question. If you look now at the planned performance of the SLS and the vehicles, all the elements getting more and more substantiated and being the best engineering estimates being replaced by actual figures, etc. If we look to the far future and talk about missions to asteroids or even other objects, are you confident that the ship is providing the mission capabilities of several weeks, even of manned missions, as you planned? Is that reassuring you?
The reality is that that long duration mission, from a consumable standpoint, Orion can fly by itself for about 4 weeks. And so the CM1 mission that Bill talked about takes us close to that level and really demonstrates the capabilities of those systems for future longer flights. We would anticipate having additional habitation capabilities, additional propulsion capabilities. But the Orion systems are being designed to those requirements, Christian, but they're also being tested to those requirements. And so we're confident today that those requirements are factored into the design of the spacecraft and that the test program will actually qualify and certify the spacecraft to all of those requirements.
So thank you very much. We have a very active audience in terms of questions. So if you don't mind, I would like to jump into the first series of questions. One of the questions here is, what was the most surprising thing you learned from this test? I mean, of course, test is supposed to run as you plan it, but sometimes things come up that you consider as very surprising, positively or negatively. What was it that struck you?
I would say, first off, what surprised me was that there were so few things to worry about, and that the ship actually performed extraordinarily well. The one failure that we had, and of course we spent all kinds of time on it since it was the one big failure, was those orange bags on the top of the spacecraft that you saw. Those are uprighting bags, and what we learned from past experience was that that shape of a capsule could land and be stable either top down in the water or bottom down in the water. And so those uprighting balloons are meant for the case where you land top down. They can flip the capsule up so the crew's not hanging from their seats waiting for the Navy divers to get to them. We think it is more of a problem with the material, the bags. Our initial reaction right at the flight time, because we'd had a few issues, was that it was somewhere in the plumbing of that system, and that ended up not being the cause at all. That surprised me.
Again, I think one thing we learned pretty positive was the processing and buildup of the vehicle in Florida, and Mike talked about that at the very beginning. You know, it's one thing on paper to look at how you build up a vehicle and add the cooling systems, and you put the thruster systems in, you do the welding and all those activities, put the wiring harnesses in. That all looks great on paper, but when you really get into manufacturing and you're doing real work, you find out things don't fit exactly right. You have problems maybe with cleanliness in some of your welding, other areas, and the teams learned a tremendous amount of I guess, lessons learned in ways to plan in a different way to be more robust. So the next time the vehicle goes through that processing in Florida, again, the vehicle for EM1 is scheduled to arrive probably next March or April, and then it begins this testing and build-up in Florida. A year from.
Don't move me up too
early.
early.
Move you up, yeah. Well, I guess it arrives right next spring, right? The 2016, excuse me, yeah,
Well,
EM1.
so the pressure vessel arrives early 2016.
And then it begins that process in Florida that I just described. So, so we'll get a chance to see if that process in Florida runs a lot smoother, which we anticipate it will because of all the things we learned on EFT1. So we'll get a chance to see how well we learn, or what we learned on EFT1 next spring. And that's what surprised me a little bit, was that was a little more maybe difficult than I would have anticipated, but it's pretty typical. I think we just haven't been in development for a while, and that's just life as you build hardware.
The other thing that I would say that surprised me a bit, and it was a positive thing, was you know, the first day of launch, we went through several cycles of trying to launch. The first was a boat encroachment in the range area. And then there were 2 other attempts, but were scrubbed because of the wind speed and direction. And the second day we were able to launch on the first attempt, but the team actually got really good at recycling the whole spacecraft, you know, in terms of going back to the point in the checklist, recycling the systems as they needed to be to really be working in conjunction with the launch vehicle team from ULA. And it was, you know, based on our shuttle experience, you don't usually recycle real quickly late in the count like that. And the team actually did really well responding to those cases on that first day of launch.
Which is probably another testing and training effect for the crew more than for the ship in the course of these kind of missions, which will be beneficial for the future flights.
Yeah, very, very much more a benefit for the whole team operation.
Talking about these kind of vehicle performance as a whole, I have a number of questions here that ask about Apollo and the shuttle, lessons learned, etc. Of course, this is now the outcome of quite a number of iterations. We've seen generally the ideas first in the Constellation program, etc., where early studies have been made. But can you maybe summarize how intensively have you looked into the shuttle and the Apollo experience, the post-flight debriefings, the lessons learned from those 2 vehicles, where you said this is really something to capture, this is what we got to incorporate, or where you have explicitly decided to say, okay, now we have new technology, we have new approaches, this is something where we implement a completely new thing?
I'll start a little bit. I think what Mike was describing earlier, the fact that we could turn around fairly quickly late in the count, is kind of a tribute to the avionics system that's set in Orion. You know, in the shuttle world, to reset computers and reset the system would be a lot more difficult, but we have effectively extremely modern avionics sitting on Orion that are conducive to allowing you to do some of this reset and turn around. The time-triggered gigabit Ethernet system that runs all the functions on board the spacecraft is a pretty sophisticated system, but it works really well. So I think the modern avionics and those kind of systems allow for some turnaround that's an improvement over what we've seen before in other vehicles.
And I would say certainly, although the capsule has the Apollo shape, the technology is all new, essentially, that builds the capsule. But this gives me an opportunity for a shout out. The Lockheed team particularly wanted to make sure that we had captured some of that Apollo experience because the team was mostly space shuttle and space station experience. And we had an opportunity to reach out to the Apollo veterans. And we actually utilized Arnie Aldrich, who's in the audience with us today, to lead a team of advisors of those Apollo veterans to help us understand what the trades were and why the trades in that era had gone one direction and perhaps ours were looking in another direction. So I think we worked hard at capturing that experience that we didn't have, but most of us had a fair amount of also shuttle and station experience. And of course, Arnie's team had a whole bunch of the early shuttle development experience as well.
And again, I think even though you saw the great performance of this vehicle, there was a lot of testing that went ahead of this vehicle flying. You know, the panels that take the load around the service module during ascent, the teams did some deploys of those ahead of time, and they found that as the pyro charge cuts along the side, it caused the panel to actually deform a little bit, and some clips were located in a place where sometimes you could get hang up, and they had to go modify some of those panels. That was discovered in an offline standalone test. So by the time you got to flight, everything worked flawlessly and performed extremely well. All the parachute activity you saw during reentry, a lot of that was demonstrated coming out of the back of an aircraft. A pretty sophisticated deploy sequence to set up the right conditions to get the drop test object to be at the right velocity. It may not even look like a capsule. Some of the test objects are more like a dart, so they actually get the higher velocity to really look at chute performance as it deploys, the reefing lines, the cutters, all that stuff we got to test ahead of time. So again, I think we learned from our past that preparing these difficult mechanical sequences and doing some standalone testing and getting that work behind you is really helpful before you get into flight. And I think it proved its worth in this test where all these systems were now integrated and they all had to work together, but those individual tests proved their worth of buying down the risk so it comes off as looking like it's a piece of cake, but it's not a piece of cake. It's a ton of work behind the scenes, doing analysis, doing tests, incremental tests, mock-up tests, et cetera, and that's what you see when you can put it together.
You just mentioned the panels and the jettison of the panels, which are in fact, and I think you said that during one of the videos, they are load-carrying panels. That's not just a fairing for aerodynamic reasons. It is a load-carrying structure, and I know from the service module that the load path from the launcher to the capsule is more complex than what we used to see in other vehicles. Can you just briefly summarize why you chose this load path, why you chose to include those panels in the load path? Is it due to the different launchers we will see, or is it, what reason does it have?
The challenge that you see in developing a spacecraft for deep space flight is how optimized mass is. And so you really want to be able to shed mass from the launch profile that you need, but you're not going to need later on. And so as the trade studies allowed us to move to the shape of the service module with the upper ring and then the slightly smaller diameter service module, we still needed to take that load path and do that in the simplest way. And that's what led to those panels actually ended up being the load path, because we shed those right after launch. We're not dragging those all the way to the moon and back, and so it's a much more mass efficient process.
Yeah, I think that's something that's really critical here. When you see some of our crew transportation vehicles that are being built for space station, they don't have nearly the mass constraints that we have here, because here every piece of mass you take with us is going all the way to the moon and coming all the way back, and that mass is tremendously important. So you have these panels, as we described, the whole service module design is optimized for weight. The heat shield performance is designed for weight. Even the new EM1 capsule that's being put together is an improvement over what was flown on EFT1. The panels and the capsule is a lighter design and construction. We've removed a couple thousand pounds of weight out of the capsule to get ready for EM1. It's fun working with our European partners on the service module. I think they're used to weight reduction, but maybe not of the magnitude that we're trying to put into this capsule. So when we go tell them that's a nice secondary bracket, but that's a low Earth orbit secondary bracket, that isn't the kind of secondary bracket we need for deep space. It needs to be a little thinner, a little lighter. And they go, well, we need to do more analysis and more work. And they go, well, we don't really want to do that. And we go, you have no choice. We're not carrying all that weight with us. Figure out a way to make it lighter and leaner. And so there's a lot of trades back and forth. So again, I think when you look at the outside of the vehicle and you look at the service module, they may all look the same, but then you got to go a little bit below and understand what's really in there and how critical weight is and what we're doing to save essentially pounds, which there's some phenomenal designs in this vehicle to just remove a couple pounds.
Now, weight is definitely an issue when you start to go, well, up in space, as always, but specifically when you go beyond low Earth orbit. So I think a big challenge will be the point in time when we put humans on board, because not only that they usually that they have their own weight, but they also take along a couple of extra items that you don't have on board with unmanned flights, like water, oxygen, etc. So one of the questions here is addressing exactly the life support system. And can you elaborate a little bit further before we come to the more philosophic questions about the future of mankind? So I would like to address this more technical question to Mike. Can you elaborate a little bit further? What are these, let's say, off-sequence tests and the preparation test of the life support system, and how will you then test it during flight?
So the big challenge with the life support system is the long-term reliability. You know, we're talking about missions that are months and years, and you can't come back home in 45 minutes or a couple days. And so you're trying to drive to not only lower mass, but also high reliability. And there are some systems, we've actually had a couple good joint developments with the ISS program that make for common systems between the two. But we have some Orion unique capabilities too. So we have a test bed in Houston that's the life support test bed, and we utilize that for the early development and testing, and then we will test all the others in their normal qualification process, first at the component level and then at the subsystem level as we get ready for flight. Bill mentioned before, some of those human systems are a little further downstream, so we haven't yet been able to start work on those, but we will see those in the development process and the testing process more in the 2018, 2019 time.
And on board station, we have the mean swing bed, which is the CO2 removal system. It's essentially a material that removes carbon dioxide. When it's exposed to vacuum, it dumps the carbon dioxide, also dumps a little bit of moisture with it. We actually flew that to space station, and we've actually been cycling and operating it on board space station. It's augmented CO2 removal on station a couple times, but that's the heart of the CO2 removal system for Orion. So we're already testing today on space station a portion of the CO2 removal system. It's not the integrated package, but it's basically the amine swing bed, and it's basically the valving system that will be used to go ahead and operate on Orion somewhere in the future. It's also neat to see the synergy between the programs. There was an Earth observation payload flown on station called RapidScat. Its purpose was to look at sea winds. So we actually took data from the space station and provided wind data for the recovery of the Orion capsule in the Pacific Ocean back to the operations team. So here's space station actually taking essentially wind data and providing it back to the ops team in Orion. Here's Orion's CO2 removal system flying on board space station, learning how to remove CO2. So in our world, we're looking at ways we can integrate across programs, use other programs to provide data, provide test sequences back and forth to get the most out of what we're doing going forward.
Yeah, and we just reached an agreement with Bill to have a common waste management system between the ISS upgrade and Orion. So there's lots of those things where we're able to start forming synergies between the programs.
So we'll have a new waste management system on board space station. It'll be used for an extended period of time, and that will be the waste management system used in Orion. So again, we get a chance to see it
No, we get the new one. We don't get the one.
Well, we'll get one or the other. We'll share.
Any plans to put animals, live animals, on one of the unmanned test flights, just to test the CO2 scrubbing or anything?
No, not at this point. You know, we've looked for considerations of metabolic simulators and things, but right now we think the sensors will give us the data that we need to characterize that environment.
Okay. Now, we're in the phase of testing and validating the vehicle, validating the data we get. Maybe we can go one step further and look into the far future when we have a fully qualified flying system, which is not only the vehicle, but we have a launcher that is performant, we have that vehicle, we have the ground segment, etc. How do you see, from your perspective, what kind of missions will we see around towards the moon, towards near-Earth objects, or eventually even up to Mars? Can you give us an outlook about this?
I can give you some suggestions and things. Again, Orion's a tremendously capable vehicle, and even Orion alone can spend 7-8 days around the moon for some kind of sortie mission, which is good, and that includes the transit time out and the transit time back for a reasonable sized crew. So if international partners are interested in doing some rover activities, maybe say on the far side of the moon, you could command those rovers using Orion as a relay down to the rovers and do some activities on the other side of the moon. There's been a lot of discussion potentially about lunar sample return. Again, Orion can play a key role in that. At some point, we'd like to get a habitation capability, again, in the vicinity of the moon. And again, we're trying to make sure that things we build today feed forward. So that habitation capability would be the habitation capability we would try to use on a Mars mission or a mission beyond the Earth-Moon system. So we'd like to get that up there. Then we can augment the stay time with Orion to be significantly longer than the number of days I described. And then we'll see what international partners want to do on the moon. There's been a lot of talk and a lot of interest from all the international community about doing things on the moon. I think we've got a very nice transportation system to get things around the moon. And when we do that, we can work with them and we can build a very nice program that keeps us moving human presence into the solar system and advancing. On the Space Launch System, we want to add as soon as we can the exploration upper stage. When we add that exploration upper stage to the Space Launch System, we now have the ability to carry roughly a 20-meter trunk behind the Orion capsule to carry cargo. We could roughly carry about 10 metric tons to the vicinity of the moon. So now in a single launch, we can carry Orion and some rudimentary 10 metric ton kind of habitation capability along with us to give us extended mission duration. So once we get to the exploration upper stage, we have a very versatile system between SLS and Orion that allows routine human presence to the vicinity of the moon to start preparing us in what we call the proving ground to get ready to go beyond the moon towards Mars or other destinations, or to support international partners if they want to do more activities on the surface of the moon. So we've got the foundation of the human exploration system well in work today. It was exciting seeing EFT-1 fly. That gives you a chance to see how far along we are. There's still a lot of work to put all these systems together, but we're building the backbone that will allow us to really move human presence into the solar system.
And from an Orion design standpoint, we do have a requirement to demonstrate to NASA at critical milestones the extensibility of the system to other capabilities and other missions. So we're in the middle of we finished the pre-board of the critical design review today. And next Wednesday is the board meeting. And so as part of that, we have a discussion about the future extensibility of the systems. And we recognize that we will very likely have some unique characteristics for each mission in the form of like a mission kit thought. But we really want the base design of the system to be stable between flights so that we don't have that cost of major extra changes.
And then another mission that you've heard us talk about is the asteroid redirect mission. The idea is to go out to a large asteroid and pull a boulder off of a large asteroid, roughly a 3 to 5 meter boulder, and then bring it into the vicinity of the moon. With Orion alone, with no other habitation capability or even an airlock, Orion is unique in the fact that you can evacuate the capsule and do a spacewalk directly out of Orion. We can actually go from Orion, send crews out to this captured boulder and actually remove samples off of the boulder and then bring them back into Orion and then return them back to the Earth. So that's another mission that's probably in the the mid-20s somewhere, 25 or so. It'll take us some time to get this boulder back using electric propulsion. And again, electric propulsion feeds forward. Its electric propulsion is needed for our Mars-class missions used to move large cargo around. We'll demonstrate moving a large boulder around, and then we'll get it in this distant retrograde orbit. So all these things we're doing all kind of are interlinked, and they all fit together, and what they're doing is building skills, building techniques, and getting us ready to keep moving human presence forward. So that'll be a pretty exciting mission when that comes about, and that's totally enabled by the Orion design we have today with very little modifications to Orion. We need to have some spacesuits, some ability to repress the cabin after we depress it for the spacewalk, but that's the only things that really need to get added to Orion. Orion can do that mission, as Mike described, with just some simple kits added.
Thank you very much. That looks pretty promising, but I could imagine that these kind of missions also call for international collaboration in one way or the other. So before we look into the political aspects of that collaboration, I would like to ask a more down-to-earth question, considering the current international cooperation we have already on that program, which is, you mentioned it, the ESA-provided service module, that part of the service module that is built in Europe. Apart from the undoubtedly extra effort it takes to integrate a new partner, to agree on similar standards, similar testing and verification approach, to manage a partner which is overseas through 2 agencies, etc. So all this is pretty clear. But could you, from your point of view, highlight 1 or 2 aspects? What does your team at Lockheed Martin benefit from that collaboration? Is there anything that you appreciate about that cooperation, also from a technical point of view?
So you already put all the hard problems aside. There are unique challenges with an international collaborative mission, pretty much that Christian captured, and we see those day in and day out. The positive that you really see from that is in that diversity of practice and thought, is that the other team is going to solve a similar problem in a very different way, and that allows you to look at your own solutions and your own processes and not always say, well, we're right and they're wrong, but it's, well, why didn't we do it that way, and why do they do it that way? And so we do have an opportunity to go through that and see that. There are certainly challenges, as you say, in terms of the management structure and the process. I think we've built, on the industry side, a very good working relationship with Airbus today. We have an Airbus liaison with our engineering team in Denver. And we now have placed a Lockheed Martin engineer with the Airbus team in Bremen. And so our ability to communicate about issues and problems is really enhanced just by that fact. But we are also on telecons and meetings with the teams every day. And that's an ongoing process. And so far we have found that that is working pretty well. We have this challenging thing called ITAR in the middle of that we get to work through. But I think we've got those processes pretty well understood and enacted right now.
Again, I think it's a vision of the future. I think we're going to do all these things cooperatively. We're going to have to learn to work together as nations. And what's interesting, it's not just cooperation. The service module is really in our critical path. We've tied our entire human spaceflight program to development of the European service module, and we're counting that much on ESA and the industry team in Europe to actually deliver this hardware to us on time for our schedules. And so that was not an easy decision for us to make, but I think our experience on station has shown the benefit of working together internationally, and having dependence upon each other is warranted, and understanding the ways each of us work gave us enough confidence we were willing to go try this. We were also smart in some ways, or we tried to be smart, where we set the interfaces, the actual hardware that interfaces directly to the capsule is still on the US side, so there's pieces there. Some of the computer interfaces were chosen such that there's a nice break between the European system and the US system. They're not fully integrated in those regions. So we kind of smartly put this together to try to structure the interfaces to be more manageable than being totally intertwined together. But it turns out as you get into the design, they're really intertwined no matter how much you try to separate them. Mike and his team are doing a great job, along with the Airbus team of really working through these issues as they head into the CDR for the service module here next year. And it's exciting seeing these teams work together and rise to the challenge. And it's not about, well, you have to change your interface or I have to change your interface. They get together as a team and they determine who can make the change on their side of the interface the easiest to keep progress moving forward. And that really is showing a maturity of this teamwork coming together.
And we've talked about the testing, and so we have the beginning of a structural test going on in the NASA facility in Plum Brook, Ohio, or in Sandusky, Ohio. We have delivered that upper ring of a structural test article already, and the ESA delivery is planned for late this month to get the rest of the system there so that they can be mated and then start into testing. And so actually 2016 is a big test year for the integrated team. And we'll see more of that. We have delivered software to the Airbus team in Les Mureaux, and they have delivered software to our team in Denver. And so we're seeing more and more of that process back and forth with the teams.
So again, I think we're really paving the way on a new level of cooperation back and forth for human spaceflight, which is really a positive thing for us globally.
Now, as we're approaching the end of this session, let's take a very broad view on this kind of collaboration and very far into the future. We have a lot of agency people here in the audience. We have young professionals. We have representatives of different companies around the world. How would you motivate all of us to think about complementary elements to that system that we just saw in order to make other missions possible? You saw that there is a lot of flexibility already built into the system, but if you had a wish list for next Christmas, what would be on that list, and what would you say to motivate people to say, come up with proposals to contribute and to add other elements so that we can have better missions, more capable missions in the future altogether?
I think, Bill hit it a little bit ago, in that we all recognize that these types of exploration missions are going to be international. No single agency or country is going to be able to marshal the resources, and probably they shouldn't try to marshal all the resources to do these complex deep space missions. So we know that it's there. Several of us have spent much of our careers already working in an international collaborative manner. So we see the positives, we see the value in building our programs that way. So I think from an encouragement standpoint, you have an ability to work with colleagues all across the globe, and that's has been for many years a motivation for me as I've been involved in these programs. Bill and I were young professionals at one point. It may have been a long time ago, but we were there. And actually, we both had an opportunity to get involved in the space station program pretty early in its development. So we've really spent years now in this international business that it is almost second nature, that you are always dealing with your colleagues around the globe. And I think that's a fascinating excitement, but it's also the motivation because that's how we're going to do these missions.
Again, I think the demands of human spaceflight always require us to work together and work as a team. Whether it's individual nation or anything, you really have to work as a team. And by working as a team, you have to trust the person that's working next to you to an unbelievable degree. And so if something's not quite going right with your schedule, even though it isn't showing up in the schedule chart, you need to be willing to share with your partner that, hey, this isn't going quite right, or if a test isn't going right, you reach out to a broad community to help you try to get information to make that test successful. And I think what we're talking about here is really raising that to the next level where we're doing it really globally. And we recognize the challenge of what we're trying to do. We're trying to move human presence beyond low Earth orbit. We've been with a sustained presence off the Earth on space station. It'll be 15 years here in November. That's a pretty big statement, but if you think about the challenges and you really decompose what it's going to take to move humans towards Mars, This is an unbelievable technology challenge for all of us, and it only will happen, I think, if we work together globally, we work together internationally, and we actually raise the bar for cooperation where we're really actively working back and forth and we really work as a seamless team. It's not about, who can minimize their cost or their schedule. It's about how you can achieve the objective in the best way and how you can take essentially whoever's got the right answer around the world, who can provide that hardware to you, can provide that new solution to your problem. You've got an amazing chance to work together. And I think what's exciting about even IAC is you get a chance to work with all the international community. The young professionals get a chance to make friends in other countries and other companies. And then when you run into a problem, you've now got a network of folks that you can reach out to and you can say, hey, we've got this design challenge. Have you ever seen anything like this? Can you help us with this design challenge? And we can rise together and really push human presence and really do these kind of bold missions like the Mars class missions we talk about somewhere in the future.
And I think we've had an opportunity as an industry team where we have reached out to major industry partners across the partnership in various ways, including our U.S. colleagues as well. And Bill's team has the ISEC-G group that meets with many agencies, more than just the space station partner agencies. And then we on the industry team frequently come and brief that body. So we're actually trading information and thoughts about mission development and interfaces and contributions through this whole process. So I think we all recognize the international fact of these missions.
Thank you very much. I think that was a very comprehensive overview of the scope and the status of the program, but also a very nice outlook to potential future. And I'm very much looking forward actually to talk next year about the first test results maybe, and see the whole vehicle coming together, the real vehicle. So I would be very happy if you would be available again next year for a similar talk or an update on that situation. But for now, I would like to thank you very much for being here with us for the past hour. That was William Gerstenmaier of NASA and Michael Hawes of Lockheed Martin, answering to many of your questions. I hope we captured or covered most of them. Thank you very much for being with us here, and enjoy the evening and the last day of the International Congress tomorrow. Thank you very much.